Okay, hello. Do you hear me? You understand me? Okay, great. Um, Welcome to the lecture Electronics for Physicists, part one. So in this semester, we will treat analog electronics from the very basics to some more difficult stuff. The lecture will be given by me and by Wolfram Erdmann. We share responsibility for this lecture. So the schedule looks like that. I will give 4 lectures in the beginning, and then Wolfram has a run with 7 lectures, and I take the last 3 again. Well, you're here, you found it. The lecture will go 13:45 till 3:30. We will take a break in the middle, and then we have the exercises also in this room, starting at 3:45. The exercises will be held by Robin Oswald and Stefan Burkhalter, our 2 very experienced assistants. And I and Wolfram are typically also available during the exercises. So if you have any questions during the lecture, please don't hesitate to ask. And if you think about a question later, you can also ask during the exercises. Okay. Well, Wolfram and I are from the Laboratory of Particle Physics at the Paul Scherrer Institute. So we come to ETH only on Fridays to give this lecture. And in our normal life, we do research at the Paul Scherrer Institute. Wolfram works in high-energy physics, and he develops very nice detectors. Is that too loud? So doing integrated circuits is his daily business. And I work on an experiment that does very accurate measurements. And so high precision electronics is my daily business. And that's why we are here and share the responsibility for this lecture. The exercises will be in 2 groups. Today we will do an introduction and do the distribution of the groups. And then we will always have a practical exercise and a simulation exercise. So half the group will do practical work and the other half will do simulation. Until about the mid of the semester, we will keep this schedule up. And the content is exactly the same. No matter if you are in group A or B, you just get it at a different week. In the end, we want to do a project, and this means that you will do a complete design cycle of an electronic circuit. This means simulating the circuit, designing the circuit in a CAD system, designing the circuit board, and then making and soldering the circuit board. And so this gives you a good impression on how a typical design cycle of an electronic system works. And these are the weeks called project here, where we will work on this practical project. Okay, I have to announce a few organizational things. We have to wear masks. The only exception is me, because we have these beautiful shields here, and it improves the understandability of the voice if I do not have to wear a mask. But if I emerge from this shield, I also will wear a mask. This lecture will be recorded, and it's available at the given link. So in principle, you can also follow, it's also possible to see the lecture online. It's an online stream also available. So it's in principle possible to follow the lecture, not in a lecture hall, but from home or from wherever. But of course, we recommend that you attend the exercises. And since there's a 15-minute break between the lecture and the exercises, it's probably best to come here and follow the lecture. Yeah, so this room is at capacity in Corona times, which means that unfortunately you will have to wear masks all the time. We will take every hour a break of 15 minutes, and during that time, we will try to get as much air exchanged as possible. It also means that you have to leave the room in the breaks. And then you should come back to the seat that you occupied before after coming back from the break. Surfaces and equipment have to be disinfected. I think this is not so important now, but as soon as we get to the practical work, we will provide disinfection wipes so that you can disinfect the equipment. Okay, electronics for physicists. Let's get into this matter. Electronics is essential for experimental physics, at least, since in principle nowadays it's impossible to take measurements or to control an experiment or to acquire data without using any kind of electronic circuit. So basically all modern experiments use electronics. It's impossible to do a modern measurement without using electronics. I thought about it quite a bit, and I didn't find an example where one would, in a non-electronic way, do a complete physics measurement. In the old days, when you took photographic plates, that you could say this is not electronic, but nowadays, a modern experiment would not be possible without electronics. And then, of course, electronics extends, you have to use them in order to extend the scale at which you can perceive things. For example, the time scale might not be accessible to human senses. If something is very fast, we just can't see it. Or if it's very, very slow, it's also difficult if you want to see a glacier moving. This is not accessible to human senses. It can also be that measurements are not accessible because of location. If you want to do a measurement on Mars, you have to control the system somewhere there. Impossible without electronics. Or it can be dangerous in high radiation zones or at high or low temperatures, which also requires you to control the experiment from a safe distance, and, well, impossible without electronics. Okay, so if we talk about electronics for physicists, typically we employ electronics to take measurements. That's at least, apart from convenience, that we want light in our lab and that we want a computer. If we talk about the physical measurement, we want to take measurements, and that could, for example, be magnetic fields with Hall sensors or flux gate sensors. Temperatures are typically measured with temperature-dependent resistance. Ionizing radiation, and this is like the whole of particle physics, uses detectors, current pulses in those detectors. Light, there are several possibilities to convert a light signal into an electronic signal. Photo effect, photocurrent, avalanche photodiodes. Pressure or sound can be measured with the piezo effect, so it's also transferring a physical signal into an electronic signal. Time, very important, can be actually measured with oscillators or comparing phase differences. And the length, so a distance, is typically measured with the travel time of sound or light, which also requires a very accurate time measurement. Okay, and then if we scale that up, if we go to a really big, complicated experiment, like the CMS experiment where Wolfram is working, there we need, well, electronics for several things. Control of the environmental parameters is an important thing. For example, you want to have a strong magnetic field in your experiment, or you need a temperature, or just control the parameters of your experiment. We often need to stimulate something in our experiments, laser pulses, alternating magnetic fields, spin rotation. And so this is also an electronic system that controls the experiment. And then nowadays, it's in principle unthinkable to do an experiment without some kind of data acquisition system that, of course, works electronically. And for example, the CMX experiment, it has like 100 million data channels. They produce like a megabyte of data every 25 nanoseconds. That's a lot of data. And so they have a pre-analysis system that reduces this to gigabytes per second, but still, I mean, this fills up whole server racks in small time. And of course, all that is unthinkable without electronics. Okay, now to define the scope of this lecture, I'd like to introduce a scale from very abstract to very detailed. And if you think about abstract, then in principle, digital signal processing is very abstract electronics. In the digital world, if you design a digital algorithm, you assume that you have ones and zeros, and that's a very abstract thing. Of course, those ones and zeros are represented by voltage levels somewhere in your processor, but you don't really care about what the actual voltage is. The only thing that counts is that you can reliably encode ones and zeros in your system, and that it does what it should do. And so this is very abstract, and this will be covered in the digital electronics course, which will be taught next semester. So if we go one level more detailed, we can think about electronic components, and at first those will be ideal components without any defects, and simplified characteristic curves. Everything will be linear, and this is just to get us into the subject. And then we can consider parasitic effects, which means that we look at the deviation from the ideal behavior. And then from that, we can go to characteristic curves, systems of differential equations, and detailed simulations of electronic systems. So this will be covered. And if we then want to go even more into the depth, we can go to a simplified physical model of what's going on, for example, in a diode or a transistor. Now, if you want to dive even deeper, then of course you have to deal with the quantum mechanics of charge transport, the Maxwell equations, if everything becomes time-dependent and oscillating. And then this is a subject for solid-state physics and electrodynamics. And we will just skim the surface of those descriptions, because this is much too detailed to build a working electronic signal. If you always think about the quantum mechanics of the transistor, then this is not something you can work with in order to get a properly designed amplifier. Okay, so this defines the scope of the lecture. We will start very basic and then go into more and more details. So nowadays, if you think about electronics, most contact that you have with electronics is digital. And I'd like to define, well, what's the difference between what we define as the difference between analog and digital electronics. Analog electronics have continuous values. It's not discrete. They're continuous in time. Typically, we have models to describe the behavior more or less accurately, and those are the characteristic curves. Small signal parameters, we will see what that is. Parasitical effects, and we do analog simulation, typically in a software called SPICE. On the other hand, digital electronics have binary, discrete signals. They're often time discretized, so synchronized to a clock. And then they are abstractly described, for example, with digital or logic description languages like VHDL and Verilog. And then there is, of course, the domain between analog and digital, so the integration of analog and digital electronics. Typically, you need that when you want to convert from analog to a digital signal and vice versa. Okay. Well, digital electronics, of course, have seen a rapid development over the last decades. And And I mean, they're so versatile. High density, many functions in one chip, large flexibility in a microcontroller on FPGA. And probably the most important thing is they're cheap. The function per the cost per function is decreasing still almost exponentially. And so, I mean, that's why we can have devices like that and everyone can afford them. If you would have to build the same device with electronics from the 1960s, it would, I don't know, fill a building and consume the power of a power plant. And the great progress that we had in digital electronics makes it possible that we can have this. So that's great. And for that reason, an increasing number of tasks are switched from that used to be analog are now digital. For example, signal processing or servo regulation, control things. And the simple reason for that is it's more flexible and cheaper. But analog electronics will always be relevant. And the simple reason is that the front end that we need as a physicist to our physical system, the microphone here, for example, this is an analog thing. And then it has to be digitized somewhere. But I mean, the first tiny signal that is produced by my voice is amplified by an analog amplifier. So everywhere where we have an interface to the physical world, we need analog electronics. Well, of course, typically then those signals are converted to digital or converted back. But that's well, also an analog design. To make a good analog to digital conversion, you need a good analog design. Okay, then power amplifiers, when the loudspeakers here, they produce an analog real-world signal. So they need to be analog, at least in the last stage. And if you want to transmit a signal, so to the radio communication that my mobile phone uses, that's of course a complicated analog design because the radio signals are analog signals. So you see this is relevant and it will always be relevant. And then of course, if you want to improve, I mean, we're talking about the large improvements that have been made in digital electronics. And those are just possible because analog electronics got better. So the digital processor, of course, each transistor is in principle an analog device. There are transistors, capacitors, and if you go very fast, waveguides. And the limitations of why don't we have a 100 gigahertz processor in a mobile phone? And the reason is because there are capacitances in this device that do not allow to switch frequencies that fast. So the limitations of those devices are because it's an analog signal. And if you want to overcome them, so I mean, if you want to design the next best processor, you have to understand all the things that go into it. And so for that also, analog electronics will always be relevant. Okay, so let's have a look at a typical signal processing chain. And so what you typically have is a physics package. And if we talk about an analog signal chain, then you have an analog input electronics, like a preamplifier. Then you could do some analog signal processing. You could filter it, gain control. You could add several signals. And a good example is this microphone system here. I mean, we have several microphones. You want to hear all of them. You don't want to hear a lot of noise, so probably they are filtered. The gain, I can control it here. So there's a certain kind of signal processing going on. And then those analog signals go to an output, a power amplifier that, for example, drives the loudspeakers. And this would be the traditional way how to do it. And in modern times, we often see that this is that the filtering, gain control, and the signal adding, for example, the signal processing, are done in digital electronics, which is probably the case for this system since I can control it with a touch screen. And so the physics package and the analog input remain the same, and then you have to have an analog to digital converter. Then you do whatever you want to do with the signal in digital, convert it back to an analog signal, and then it goes through the output electronics. And well, that's the more modern way to do it. And for example, you could have a temperature sensor that controls a motor, I don't know, which closes the blinds. Or you could have a photodiode that controls the power of a laser also. And those signal processing things are nowadays often in digital electronics, which of course makes it more flexible. There are some things you cannot do in analog, but everything you can do in analog, you can also simulate in digital. Except if you want to be really, really, really fast, then it might be, this might not be possible at any speed. Okay, anyway, this part here in the middle, the blue part, will be covered in part 2 of this lecture. And this will be in the spring semester, of course, not of 2020, but 2021. Okay, let's have a look at an example. This is an example of a CMS pixel module. And here you see analog and digital electronics mixed. For example, this here is an FPGA. So it's a configurable digital circuit. You see many connectors where signals come in. So this is a digital connector, those are analog connectors. Then you see a lot of components that are necessary to supply the power, the correct voltages to all those devices, like DC-DC converters, voltage regulators. And there is a custom ASIC on this thing. Wolfram, help me, is it this one? Okay. So it's a digital circuit that was just designed for the, or is it digital? I don't know. Just designed for this one experiment, and this is a bit special, that you can design chips just to do one special function in an experiment. Okay, and then of course converters between analog and digital are on this system. Okay, now let's come to the goals of this lecture. So we want to explain the basic concepts and phenomena, and we will start really basic, I mean like resistors and so on. Then the functionality and properties of electronic components, we will take a look at them individually. And then we will combine those electronic components to circuits, understand electronic circuits, and go through different levels of circuit analysis. This is like the mathematical basis of how to get from I draw an electronic circuit to I understand what's going on. Another goal is to become fluent in the language of electronics. So even if, I don't know, if you do a PhD thesis and your experiment requires a special electronic setup that doesn't exist, so you have to build it, then probably you will build it together with an electrical engineer or a technician who do that all the time. But it helps enormously if you know the technical terms and speak the language of those people so that you can communicate efficiently. And for that, it's really important to have it, I mean, to do the process once yourself and be fluent in the language of electronics. Okay, in the exercises, as I said, we will give you some hands-on experience so you can build circuits yourself. We will also have, as I said, a part based on simulation. And for that, we use the program called SPICE, which is simulation program with integrated circuits emphasis, but we will not use it for integrated circuits, but for discrete circuits. And as I said, we will do a small project. Okay, so let me come to the outline. So we will go through the really basics of electronics, like electronic charge, current, voltage, resistance, and then go into the analysis of simple electronic networks. Then we have a look at all the passive components, resistors, capacitors, inductors. Go into time and frequency dependent processes, transmission lines, then the first semiconductors, diodes, transistors, first the bipolar and the basic transistor circuits. Then we will go into more advanced amplifiers, for example, the difference amplifier or the operational amplifier. Then we cover, or actually Wolfram does, field effect transistors, so different kind of transistor. We will talk about modulation, which is an important concept in electronics. And then there will be a segment about noise and electronic circuits, noise in electronic circuits, and analog filters. And in the end, analog to digital and digital to analog converters. And then this is the natural transition to the next lecture, where the digital part will be covered. Okay, so let's dive right in. Of course, you all know that electronics is done with electric charge. The unit of charge is the coulomb. Of course, the elementary charge is the electron charge with something like 1.6 times 10 to the 19 coulombs. And the charge is the source of the electric field. All of that should not be new to you, is it? No, good. Yeah, important is the charge density, which is the source term of the electric field. And we have charge conservation. Charge is not created or destroyed, at least not in the experiment we do. So charge is constant in everything we do. And of course, we have to take polarity into account. Okay, let's come to current. Current is moving charges. And the effective amount of a charge, so it could be a small portion of the charges that move during a time through an area. This defines a current. It's the moving charge per time unit. And of course, the unit of the current is amperes, which is coulombs per second, so it quantifies the charge that moves in a certain time. Yeah, okay, first convention, this one is easy. The sign convention of the current, we use a positive current would be the motion of positive charges, right? The motion of direction, the direction of motion of positive charges. Since most of our electronics is done with electrons, the actual direction of motion of the electrons is in the opposite direction. Oops. Which is, of course, clear. Of course, in semiconductors, we can have positive charges, and there then the current direction is the same as the direction of the charge movement. Actually, this was defined before the value of the charge of the electron was known, and we never changed it. Yeah, then an important quantity is the current density. It's the current per unit area. So it has units of amperes per square meter. And of course, the current is the current density times this area. Okay, now with this, we can have a look at how charge moves through a conductor. So the defining equation is given here. The current is proportional to the area, to the density of the charges, the charge, of course, per charge carrier, and the average velocity of those charges. And in a metal, the number or the density of charges that we have is comparable to the density of atoms that we have. So it's incredibly large. So there's a huge amount of charges that can move, and if we get them to move, this already is a large current. In a semiconductor, some electrons can move, and some electron holes. So actually it's a spot where an electron is missing, which is effectively a positive charge that moves. They are free to move, but the number of charge carriers is much, much, much smaller than the number of atoms. And it's a strong dependence on temperature. And then, of course, in an electrolyte, in a liquid, you can have some movable ions. They can be positive or negative, but of course also a much smaller density of charge carriers than in the metal. Yeah, orders of magnitude for current, pico to nanoampere. This is something we have now in semiconductor sensors or leakage currents. So these are very small effects. Microamperes are typical currents in transistors or highly integrated circuits. And milliampere is something you would have in a small discrete transistor. It's the current that makes an LED shine a few milliamperes. If we talk about amperes, it's already power electronics. And if we talk about kiloamperes, this is really high power stuff. So it's either something very special, or if you want to make an electrical train move, you need kiloampere currents, and in order to control them, you need special electronics called thyristors, for example. Yeah, current consists, of course, of charge carriers. But since the electrons have such a small charge, it's always a large number of electrons that make up our current. So if we have 1 ampere, it's 10 to the 18 electrons per second. It's an unbelievably large number. If you have a picoampere, it's already, it's 10 to the 6 electrons per second, and it's 1 electron per microsecond. So a picoampere is a small current, but remember, if you want to measure a picoampere with microsecond time resolution, you are looking at individual electrons passing through your detector. So this might be difficult to detect. Just to give you an idea. And of course, if you are down in current to individually moving charge carriers, then you get statistical fluctuations. It's called shot noise. We will have a look at shot noise later when we discuss noise in electronic circuits. Okay, so that's it about current. What makes the current go through a conductor is the voltage. Voltage is defined as a potential difference between two electric potentials. And well, you can say it's the energy gain of a positive elementary charge when it moves from one potential to the other potential. It's a conservative potential, so it does not depend on the path, at least if we talk about non-time varying electromagnetic fields. And the voltage is simply defined as the difference in electric potential between these two surfaces. There is, of course, a sign convention here. A positive voltage makes a positive charge accelerate towards the negative end, which of course is clear if this is positively charged and we have a positive charge here, it's repelled by this. It attracts to this one here, and so of course it wants to go this direction. And again, this is done with it's defined with a positive test charge. And for that reason, as I said, the current direction is based on positive charges. Okay. Yeah. Voltage in principle is only defined as a potential difference. And now, in order to make our life easy in electronic circuits, we define zero somewhere. And then you can talk about that a certain line has a certain voltage, yeah? Which means that before we can say that, we have to define where zero is. And so we define zero as the ground level. So the potential of 0 volts can be called ground, GND. It can have this or this symbol. And then voltage levels in a schematic are always given with respect to 0. So it's always to be understood as a voltage difference between the reference point that you have defined somewhere and the voltage that is given. That's also important for simulations. If you tell a computer to simulate voltage levels, you have to tell it where 0 is. And for that reason, for example, in SPICE, you have to have a node 0 where the program knows, okay, this is 0 potential. We typically don't call the potential of a voltage somewhere in the circuit the electric potential, but the voltage, and it's either a U or a V. The ground that defines 0 potential in a circuit is not necessarily the same thing as the ground connection that you have in the mains connector. The ground in the mains connector is a safety precaution that makes interrupts the circuit as soon as a current goes through this ground connection. The ground in an electronic scheme can carry any current. Yeah. And there are circuits where these two are connected at some point, but it's not necessarily the case. Okay, yeah, let's talk about how electrons move in a conductor. So at 0 electric field, electrons simply move because the temperature is not 0. There's a small thermal excitation, and they do a random motion through the conductor, random Brownian motion, and this gives rise to thermal noise. If we now enable an electric field in some direction, then in addition to this Brownian random motion, we get a drift. And you can think about the motion in a conductor that the electrons are accelerated by the electric field. There's the electric field in the conductor. They are accelerated, and why don't they accelerate until they have infinite velocity? Because they collide with something. They lose all their kinetic energy, so they collide with an atom, and then are accelerated again. And so what happens is that for the average velocity that an electron has is something like the average velocity that is the interplay between accelerating an electric field and hitting something and being brought to rest, so to say. Of course, the effect of an electrical resistance is how likely it is that the electron collides with something. So in a good conductor, the electron can go for a small distance and then lose its energy. In a bad conductor, it collides very quickly. And of course, every time it collides with the rest of the, for example, with an atom, it loses its energy, and this energy goes into heat in the conductor, and that's why conductors heat up. If you have a superconductor, then this doesn't happen. That's the 3-path length goes to infinity. Okay, so what we can say is that this average velocity is proportional to the electric field in a rough sense, and we just call the constant of proportionality to mobility. Okay, now we can, from this concept of that a voltage difference leads to a average drift velocity of our charge carriers. From that, we can compute the resistance of a certain conductor. So we can write the current, as we have done before, as the cross-section area times the charge carrier density times the charge of the charge carriers and times the average velocity. And now we insert this material constant as the velocity. And we replace the electric field with the voltage difference, the potential difference, divided by the length. This is the definition of an electric field. So if we put this in, we see that the current is proportional to the cross-section divided by the length, and then times some constants that depend on the material, and then times the voltage. Now, these constants we put together in one quantity, and then we see that the cross-section divided by the length is something that's defined by the shape of our conductor, and all the rest is defined by the properties of the material. And then, of course, it's proportional to the voltage. So geometrical parameters, that's clear. And then this sigma parameter is a property of the material called electrical conductivity. The conductivity gives us, for example, if we don't want to care about the geometry of the conductor, we can directly go to current density, and then the conductivity directly gives us the current density if we multiply with electric field. The unit of conductivity is Siemens per meter, and Siemens is simply inverse ohms. We can just write the exact same thing using the resistivity. So we replace the sigma with a 1 over rho, and for that reason the units are also the exact inverse, so it's ohms times meter. But this is the same thing. If you know sigma, you can calculate rho just by taking the reciprocal value. And then if you have a concrete piece of resistor, you can characterize its properties with the resistance. Of course, the unit is ohms. And then we find, of course, the Ohm's law that the current is proportional to the voltage divided by the resistance. Material constants, either expressed as the resistivity or the conductivity. And you can convert, of course, the resistance into a conductivity or resistivity if you know the geometrical shape of your conductor. For semiconductors, the resistivity is an important quantity. It's one of the things that you can tune in a semiconductor. And it's often given in ohm centimeters because meters is such a long distance. Okay, and of course, it should not be new to you that Ohm's law can be written like this, that the current is proportional to the voltage in both forms. If you want to extract the current, you have to take 1 over the resistance. If you want to extract the voltage, its voltage is equal resistance times current. Okay. Different materials, of course, have very different conductivities. The best you can have is silver, and then copper, aluminum, platinum, bismuth are all good conductors. Then you have the whole range of semiconductors, and you see this is an logarithmic scale, and from here to here, this is 8 orders of magnitude. So, I mean, the semiconductor conductivity you can change over something like 10 orders of magnitude. This is a huge range. Um, and then even further, even lower conductivity or higher resistivity are then the insulators. And you see also here, it's like many orders of magnitude that you can find in different materials. The cool thing is that from this whole chart covers 24 orders of magnitude. So that's an incredible large range of values that you find in conductivity. And in principle, we could build all our electronic circuits not with electrical fields, but with magnetic fields. In principle, there's nothing that would stop us from not building an electronic circuit, but magnetronic circuits. The only thing that's missing is that we cannot control magnetic fields. We cannot guide magnetic fields because we do not have such a large difference between a magnetic conductor and a magnetic insulator. The best magnetic insulator we have is vacuum, has a susceptibility of 1. And the best magnetic conductors we have is, I don't know, some special iron alloy. And maybe you can get a conductivity of 10 to the 6, 1 million. Yeah. So 6 orders of magnitude. We can vary magnetic conductivity by 6 orders of magnitude. Yeah. And for electronic conductivity, we have 24 orders of magnitude. So this is why electronics is much more usable to control things than magnetic fields. Okay, so that's the reason why the lecture is called electronics. And after the break, we will go more into resistors. I will ask you to leave the lecture hall now. We will try to exchange as much air as possible. And please be back 2:45. Okay, let's continue. I'd like quickly to cover the temperature dependence of electrical resistance. And as you see here, for a normal conductor with rising temperature, the resistivity rises. And well, a hand-waving model how to explain that would be, imagine that an electron is now accelerated by the electric field. And there is, at low temperatures, the atom with which it could collide is at rest. So it can go past it. At higher temperatures, this atom is moving itself, so it's a larger target. And for that reason, the probability to hit it is larger. And for that reason, the electron is like, has a larger friction and doesn't move as quickly. The same effect is also present in semiconductors, but in semiconductors, there is a different effect that dominates this completely. And in semiconductors, the density of charge carriers is temperature dependent. And so that the resistance increases because the free path length decreases a little bit. Is not so important in semiconductors because it's just compensated by the exponential growth of charge carriers with temperature. And so in semiconductors with increasing temperature, the resistivity decreases. Okay, now this covers the introduction to charge and resistance. Do you have questions at this point? Okay, seems not to be the case. Also, if you think about questions later, you can ask during the exercises. The next subject I would like to go into is network analysis, and let's define what a network is. A network is, electrical components connected by wires. The the electrical components itself can be n-poles, so there's a two-pole component here, it has two connections, or this thing has four connections, it's a four-pole. And in principle, there can be, again, an electrical network inside. So it's an abstract picture of what an electrical component can be. And it's just, basically termed by the number of connections it has to the outside. Connections are ideal conductors, so they have no resistance and there's no delay if a signal emerges here, it's immediately visible at this point. It's important that for network analysis we rely on the fact that there are no additional interactions. So if you have a real electronic system somewhere and you put a conductor close to it, for example, some of the magnetic field of this conductor might have an influence on the electronic component that we have here. And this we cannot model in such a circuit if these two things are separate. If we want to model it, we have to add additional components that like mediate this interaction. The same is true for other imperfections. So if a connection has a resistance, then we have to put a resistor. These lines that we draw, as I said, are ideal conductors. Yeah, and then we have connection points called nodes. And in principle, the whole point of network analysis is to understand what's going on at a certain node, given certain conditions. And so for the first part of the lecture, we will talk about linear passive components. So let's define what linear is. Linear means that if the current changes by a certain scaling factor, then also the voltage changes by the same scaling factor. So for example, if we have calculated the voltage that is necessary to drive, let's go like this, the voltage that is necessary to drive a certain current, and then we also determined the voltage that is necessary to drive a certain other current, then the voltage to drive these two currents together, we can simply add up these two results. That's clear if you think about Ohm's law. If you have a 1 ohm resistor and you want to drive 1 ampere, you need 1 volt. That's clear. If you want to drive 5 amperes, you need 5 volts. Now we can add the two. If we want to drive 6 amperes, we need 6 volts. So it's for resistors, it's clear they are linear components. And it's also true for capacitors and inductors. Yeah, let's talk about resistors. A resistor, a power resistor can look like this, but typical resistors look like that. And if you use surface mount components, they still look different. The symbol we use for resistors is typically such a box with an R, or in the American literature, it's this wiggly line. Of course, for a resistor, we know Ohm's law applies, and there is a nice correspondence to the law for a spring, where we also have the length proportional to the force. So here we have voltage proportional to current times resistance. Now this is an ideal resistor, and if we want to describe a resistor that more corresponds to a real resistor that we would find, I mean, if you just take this component and you measure all its quantities very carefully, you find that it has a certain small capacity associated with it, or a small inductance. And so in order to model this in circuit analysis, we have to add these additional components if it's interesting for this particular case. And then the resistor becomes all this, as we call, parasitic properties as well. So this would be a parasitic capacitance, and this would be a parasitic inductance. Now, given that these other components, they have frequency-dependent resistances, so to say, and this means that the Ohm's law is only valid at small frequencies. And if you want to use a resistor at a high frequency, you have to be aware that the resistance might change, and you have to compute with complex resistances or impedances. And this is an important subject that we will cover in a later lecture. There is important sign conventions for circuit analysis. And unfortunately, until now, the sign conventions were all defined. So current is defined as the direction of motion of positive charge. And for the signs that denote voltage differences measured across a resistor, unfortunately, there is not a universal sign convention. So if you typically it's indicated by an arrow across the component. So if you have a current going in a certain direction, indicated by this arrow here, then one convention is that this arrow here is parallel to this one. And this is clear. Ohm's law tells us that these two quantities are proportional to each other, if this is a simple resistor. And this also means that they go in the same direction. So from that point of view, this convention is practical. You can also say, okay, I denote it with plus and minus signs. And well, we know positive current goes from plus to minus. And so this current arrow here is consistent with this plus and minus denotion across the component here. Sometimes it's indicated with an arrow that has two arrowheads, and then you have to have a plus and minus in order to know what this voltage difference, what's the polarity convention for this voltage difference. And then it also is possible to see the plus and minus sign with an arrow that is reversed. So this arrow points from minus to plus, which is also a nice convention, but then it's reversed to the current, and sometimes the plus and minus is not written. So there's a whole lot of different conventions. For example, depending which textbook you use or which software you use, it might be one of them. The important thing is that Ohm's law always applies. So if you have something like this potential difference here, so higher potential here, lower potential here, then the positive current always goes from plus to minus. And this is in principle the thing that has to be correct every time. And so this helps you to figure out what the convention is that a certain textbook uses. Okay, now let's send a current through a resistor, and in order to do that we need a voltage source. So this is our next symbol, the ideal voltage source, characterized of course by the voltage that it generates, and here in this symbol plus and minus sign are given, so polarity is well defined. And then it's clear that from the plus connection of the voltage source, the current goes through whatever we connect to it, in this case just a single resistor, and then into the minus sign of the voltage source. There are also alternative symbols. For example, this equal sign here means that it's a DC current source, so a constant voltage or current. And of course, the voltage source is characterized by its voltage. It's independent of current. So the ideal voltage source can supply any current we want. So if we connect a micro ohm resistor here, then a very, very large current will flow. And the ideal voltage source is not limited. So it delivers arbitrary large currents. There's no power limit. The series connection of voltage sources is well defined. So if you have one voltage source, another voltage source, you connect them in series, then you simply add the two voltages. The parallel connection of two voltage sources, of two ideal voltage sources, is not defined. Because each voltage source, if you have one and you put another one in parallel, each of them will try, well, by definition, achieves the voltage that it's set to across its terminals. Now, unless the voltage is exactly the same, then of course it's possible, then it's just the voltage you set. But if one has a different voltage than the other, it's impossible, it's not defined what will happen. But since there are no ideal voltage sources in the world, we can, well, this is not a real problem. It's just a problem in simulations. If you define two ideal voltage sources in parallel, the simulation will tell this is an error, I cannot compute this. Okay, as I said, the direction of the voltage error is often anti-parallel to the direction of the current. You see that the current goes this way, and the direction of this arrow here is from plus to minus. Well, different convention, as said, is used in English-speaking countries, and the program that we recommend to use for the simulations, KiCad, for example, uses a different convention. Okay, let's talk about a real voltage source. And this is like the first thing where we talk about practical implementation of electronics, which I think is important to know about, since if you are in the lab, there is no ideal voltage source. So the only thing that we have to change is that we take an ideal voltage source and we add one more resistor. This resistor is called the internal resistance, Innenwiderstand, and it changes the behavior of the voltage source. Now, if we connect a large resistance here, this means we have a small current, Ohm's law. Then the voltage here, if you see this diagram, the voltage is almost the correct voltage. It's almost the same behavior as the ideal voltage source. If we now make this resistance here smaller and smaller, then the current will get larger and larger. And so we go along this curve, we deviate from the ideal voltage source because there is a voltage drop across this resistor. Is that clear if I say a current produces a voltage drop? Yes, to everyone? Great. Okay. So simply Ohm's law, this resistor, there's a current going through it, so the voltage here and here have to have a different value. So we lose a little bit of the voltage in this resistor. And then, of course, this would go on forever. But if you have a real voltage source, there is a power limit somewhere. And so as soon as you increase the current to above that limit, the voltage will drop even more. And the current source will simply collapse and not deliver any more voltage. Well, this is when your experiment starts to fail. So yeah, the current drops with increasing load, increasing current. And yeah, we can calculate the internal resistance by defining the slope in this diagram. So voltage current deviation or slope. Yeah, there's often a current limit, can also be adjustable. It's a good idea to, if you connect a new circuit board to your power supply, to first of all set a current limit so that it doesn't supply all its power if you don't know if the circuit works or not. And of course, examples are our benchtop power supplies that you have in the lab, or batteries, voltage regulators, DC-DC converters, which are in principle small power supplies where you go in with a DC voltage, you come out with a DC voltage, and in between there are electronics that convert different voltage levels. Also important is signal sources, function generators, even more so because they typically have larger internal resistances. And so if you do not take this into account, the signal level that you get on the output of a function generator might not be what you expect. Okay, yeah, let's come to current sources. It's the same thing, just that many aspects between current and voltage are reversed, and we will see many examples during the lecture that there's a certain symmetry between current laws and voltage laws, and that it's typically that if something is like that with a voltage, then it's the reciprocal thing with the current. And so, yeah, a current source provides a current independent of the load resistance. The deviation or the slope of the voltage to current is infinite, not zero, which in principle means that it has an infinite internal resistance. It generates arbitrarily large voltages to maintain the current that is set. Yeah? So if we make this resistance really large, a mega ohm, and we want to drive 1 ampere, then we have to supply a megavolt. Yeah? And the ideal current source will provide any voltage to just drive the current that we have set it to. Of course, this is not the case in reality. The parallel connection of current sources leads to adding the two currents, and the serial connection is not defined. You see, this is the exact opposite with current sources. Current sources we can connect in series, and that is well defined. Current sources we can connect in parallel in order to add the currents. Okay, a real current source then again has just a resistor added to it in order to make it realistic. And the difference is that this resistor is now parallel to the load resistor. And so a portion of the current goes through here. If the voltage that is needed to drive the current here gets large, then a larger and larger part of the current branches through this internal resistance. So which means that the current that we get out of the current source drops with increasing load. And in this case, increasing load means increasing compliance voltage. So the higher the voltage is that has to be generated to drive the current, the more we deviate from the ideal behavior. The equivalent model is, again, this internal resistance. And the difference is that the ideal current source has an infinite internal resistance. And if it's not infinite, then no, that's not true. Zero internal resistance. No, infinite. Yeah, okay. Yes. So this behavior here, okay, this is the other way around, is ideal if this is infinite. And then, of course, you can have a voltage limitation, simply also something that you adjust on the benchtop power supply if you set a voltage. And if the compliance voltage that is necessary to drive the current exceeds that voltage limit, then the current will simply not be able to increase. Okay, now this gives us the components that are necessary to do network analysis. So that's the basic thing that we need in order to understand electronic circuits. And basically this was pioneered by Gustav Robert Kirchhoff. And what he came up with is a nice set of rules that in principle any combination of current sources, voltage sources, and resistors, and later we will have more components, can be combined in a network, arbitrarily complex, and it's a set of rules that helps you to determine what's going on. So the goal is to determine voltages and currents in the network. And what we need is Kirchhoff's circuit laws. And then there are in principle three methods how to do that. The nodal analysis, the mesh analysis, and the superposition theorem. So in German Knotenpotentialverfahren, Maschenstromverfahren und Überlagerungsverfahren. And they all provide the same answer, of course, it's the same circuit. But they take it's a different concept how to get to the answer. And later it will be seen that there are some circuits for which one of the methods is easier than others. Okay, so let's come to the Kirchhoff rules. Kirchhoff's current law, Knotenregel, says that the sum of all currents meeting in a node is zero. Now, this is clear because of the conservation of charge. So if you think about, we cannot create charge, so every charge carrier that goes into a connection, like this one, has to come out somewhere. Important is that we have to have a consistent sign convention. So in this example, all currents are counted as positive if they go into the node. Yeah? And then this simple formula is valid that some of the currents can be positive and then others have to be negative in order to balance out the sum to 0. If you define the direction of your currents differently, then you have to take into account which direction the currents have. And in this example, for example, current 1 and current 4 go into the node, and current 3 and current 2 come out of the node. And for that reason, we have to count current 1 and current 4 with a positive sign, and current 2 and 3 with negative signs. And yes, typically you would not change the arrow direction of your currents in your schematic. So this will happen all the time, that we have to count currents with a different polarity depending on which node we look at. And this is important to see. One more thing to say, that the values of the currents can be positive or negative, independent on how the direction of the arrow is drawn. So what you would typically do is when you draw a schematic, you basically define the current direction by indicating arrows. And then you calculate what's going on, and it can be that the current that results actually flows in the other direction. And this simply means that the current that you have at certain segment is negative. Yeah. And if you have a bit of experience, you can always make one can try to make the arrows already from the start in a way that they're all positive, but in some examples that's just not possible. Okay, charge conservation is the basic principle behind this law, and so let's talk about that a bit. It's valid in all electrical components. So it doesn't matter if it's a resistor or a power supply or a capacitor. The current that goes in comes out. Or let's say the sum of all currents that go in have to be equal to the sum of all currents that come out. This is true at all times. I must say this is strictly true for all times that are longer, well, time intervals that are longer than the travel time of light through the component. So the electromagnetic interaction is mediated by the electromagnetic force, and the electromagnetic force has a finite velocity, and so it's, if you take, for example, a long conductor, it's possible to send in a signal, and it takes a nanosecond for it to come out. So if you look at the situation nanosecond by nanosecond, then this rule is not true. If you look at the signal second by second, it's always true. Okay, unless you have conductors that are, I don't know, a transmission line to the moon or so. Okay, but I mean, for all practical purposes, on our electronic circuit boards and for all practical timescales that we will be looking at, it's always true that the current that goes in comes out. This also applies to capacitors. Yeah? People often say that a capacitor is being charged. And I mean, you could think about it as, I mean, a current going in, and then it charges up, and only when it's charged up, the current comes out. Like in a bathtub that you fill up, and only when you have reached the top level, then it spills over. But this is not true. In a capacitor, when a charge carrier goes in, an electron goes in, it replaces an electron, or that has to be pushed out immediately. And again, this is mediated by electromagnetic forces. So on timescales longer than it takes for the electromagnetic force to do its work, this is always true. Yeah, if a component seems to collect charge or seems to lose charge, then there must be an additional connection. Yeah? For example, there could be a capacitor that is charged and loses charge, and it doesn't appear anywhere in your system. And then there could be a leakage current to the box of the device or so. And well, yeah, this then means that in order to model this correctly in our schematic, we have to draw one more resistor, for example, with a high resistance, a mega ohm, to the ground of the experiment. Yeah, you can think about charge conservation as there's a nice correspondence to an incompressible liquid. So if you have tubes that are completely filled with a liquid that cannot be compressed, then no matter what you want to do, you can push the liquid through the tubes. But as soon as you have pushed something into a certain kind of, I mean, it doesn't matter how complicated the tubes are, if you push it in, it has to come out somewhere. It's not compressible. Yeah? And if it spills out of the system somewhere, then you have forgotten to take some connection into account. Okay, the second Kirchhoff's law is Kirchhoff's voltage law. And it simply says that the sum of all voltages in a mesh, so a mesh is a connection of components that build a closed circle. The sum of all voltages in a mesh is 0. And it's easy to see why this has to be the case. Otherwise, conservation of energy would not be fulfilled. If the sum of the voltages in this mesh would be different than 0, then we could run a charge through them. And the definition of a voltage is that a charge gains energy when we go through a voltage difference. Yeah? So we would gain energy by going through the circle, and then we would end up at the same point at a higher energy. And then we could go through the circle again and again add some energy to our charge. And then, of course, the current would become infinitely large because all the charges get accelerated more and more. So, of course, this cannot be true. And for that reason, the sum of all these voltages has to be 0. Again, here we have to think about the sign convention in order to make this useful. And here in this case, we define a sense of rotation and have all the sign conventions, in this case, parallel to the sense of rotation. If the sign conventions in your schematic are different, so for example, U1 is parallel to the sense of rotation, U2 is also parallel to the sense of convention, U3 is anti-parallel, and U4 is again parallel, and then we have to count 1 and 2 positive, 3 negative, and 4 positive again. Simply a thing you have to take into account. Okay, yeah, these are the 2 rules that Kirchhoff came up with, and that's everything you need to analyze, in principle, arbitrarily complex electronic circuits. So let's review that. There is the voltage law. The sum of all voltages in a mesh is 0. And there's the current law. The sum of all currents that go into a node is also 0. Okay, let's apply that to find out what's going on in this circuit. So we have 2 voltage sources here, and then 3 resistors connected such that we build 2 meshes. This is one mesh, this is one mesh, and then we have 2 non-trivial nodes, one node here, one node here. And well, the goal of circuit analysis is to determine all currents, for example, as a function of the voltages that you apply at the voltage sources. And well, the method is to use the voltage and current laws to gain enough independent equations and then solve the system of equations. Okay, so let's do this with the current law. Now, here you see the nodes numbered, node 0 here. What's going on here? So we have the current I3 going into this node. So this we call positively. And then we have to follow this. We have to follow this. We said that the current goes through a component without being changed. So the current that goes in is the same as the one that goes out. So the current that comes out of the node here is current IQ1. So it's the current through source 1. And since it comes out of the node, we count it negatively. The same is true for IQ2. So we follow this line. We go through the component. Component does not change the current. And find that the direction is out of this node. So we also count it negatively. It's IQ2. Then we have some, the next interesting node is node 1. Here we see that current 2 and current 1 go into the node, and current 3 comes out of the node. So we call 1 and 2 positively, and current 3 we count negatively. And then we have two trivial nodes. This current here, IQ1, goes into node 2, and there is no other connection, so it has to come out here. The resistor does not change the current, so it's the same as current 1. And written as the current law for this node means that the incoming current minus the outgoing current has to be 0. And of course, that's equivalent to saying that this current is the same as that current. Same is true here. The current coming out of voltage source 2 goes through the resistor and has to be equal to current 2. Okay. Now, we can put these two identities into the first equation, and then we see that the first and the second equations basically say the same thing, that the sum of currents 1 and 2 is equal to current 3. Basic thing. If you, of course, doubt this is trivial, if you have a more complicated system, then it takes a bit more figuring out to come up with all independent equations you can find for your currents. Okay, now we apply the voltage law. So first of all, we have to define the polarity of the voltages. For the current sources, that's defined. And then for the resistors, we define the voltage direction, so to say, parallel to the current direction. And then we can have a look at the two meshes. So for mesh A, we define a sense of rotation, in this case, positive mathematical rotation sense, and see that this voltage here over resistor R3, the sense of rotation is different than this, so we count it negatively. And we immediately apply Ohm's law. The voltage across R3 is, of course, R3 times I3. So we call negatively R3 times I3. Then we do the same for resistor 1. It's also this sense of rotation is against, or this definition is against our sense of rotation, so we call it negatively. And finally, for the voltage source, it's the same direction as our sense of rotation, so we call it positively. This gives us an equation describing the voltages in this mesh. And in the other mesh, we do the exact same thing and get a very similar expression. Now, we use the result that we achieved on one slide before in order to replace current 3 with current 1 and 2 and get this system of equations. And now what we have is two equations, and we said we want to determine the two currents, or we want, yeah. And so we have two unknowns. And of course, this is solvable. It's advantageous to write this as a matrix. So yeah, solve for the voltages, put them on one side, and then everything that is related to current 2, you write in a row, everything related to current 1, you write in a row. And then this can be written as a matrix multiplication of a current vector equaling a voltage vector. Yeah, using the general solution for an inverse matrix, we then can determine current 1 and current 2 and use again the relation between these and current 3 and come up with this equation. Now, this is not the most trivial expression if you want to combine voltages and resistances. You see, of course, the general resistance goes up if we increase voltage 1. It goes up if we increase voltage 2, but then already the weighting factors defined by those resistances here is a bit complicated. And of course, we chose the example to show a non-trivial thing. Now, probably going through the math like that is a bit too fast to follow in the lecture. And I encourage you to go through this once for yourself. In later lectures, we will speed this up quite a bit. And then I will simply say, okay, I mean, the solution to this circuit yields this and that. I will always give in the lecture enough details or enough results, intermediate results, that you can check your own calculation. But I think you learn a lot about how to manipulate and work with those components if you do the calculations on a piece of paper for yourself. So I encourage you to do that, and then it will become clear how this whole method of symbolic network analysis works. Okay, next lecture we will talk about the two other methods proposed by Kirchhoff to solve the same network, and of course we will gain the same result. And that's it for today. Thank you. So now, if you have questions, this would now be a good time. Otherwise, you can also ask during the exercises. We will do another. Was meinst du, Robin? Brauchen wir eine Pause? Okay, so for today, we simply do the distribution of the exercise groups and do a short introduction. And so today we don't do a break. But of course, usually we would do a break in order to exchange air in the room. So yeah, thank you.
Sorry for the small delay. I'm Robin Oswald, and I'm a PhD student, mainly working actually with trapped ions, but while doing so, also doing a lot of electronics. And I'll be one of the assistants, guiding one part, and the other one is Stefan Burkhalter at the back. And today, I just want to quickly talk a little bit about the organization of the exercise classes, which would usually take place now for roughly 2-ish hours. If it takes a little bit longer, it's also not that much of a deal. I guess anyways, now we have to be somewhat flexible. But today it's only a short introduction. And maybe I'm going to start with some motivation. Here you can see an admittedly somewhat bad picture of the lab I'm usually working in. I would say the main takeaway from this is you see that at normal table level, it's a table filled with optical elements, but from like shoulder level and up, it's all filled with electronic devices that somehow monitor or babysit or control or record all the optics that's going on. So even though you might not have to build all these individual devices yourself, you certainly have to choose which ones to get, buy, and then somehow make them play nice together. So that's another motivation, both for taking this lecture, I guess, but then also for getting your hands dirty in the practical aspect, because there are many little small things that can go between the cracks. So if you buy the fanciest, best device, but then are too stupid to use it correctly, it's kind of sad. So we want to prevent this. And on the left-hand side, I just put a few keywords that right now you don't really need to know. But if you do any kind of work in the lab, eventually you'll stumble upon it. And I think we'll cover most of these both in the analog lecture and then the follow-on digital part. So that's kind of the world where I mostly live in, where I can mostly buy devices and just make them play nice together. And occasionally the device I want doesn't exist or doesn't exist at the price point I want, so then I have to make my own. For Stefan, it's somewhat different because they're doing the detectors at CERN, and I guess they would love to be able to just buy what they needed, but it just doesn't exist, so they're forced to do it all themselves. The main difference being that then a lot of the luxuries I have of buying either devices or really nice integrated circuits that already do all the stuff I want, and I just have to kind of glue them together, doesn't exist anymore for him, and you have to go quite a few layers deeper. And I think in this lecture we'll have a reasonable mix between both worlds, so you'll get to see a little bit of both. And I think it's also important to get a feeling yourself for what already exists out there and what you can buy and what you really have to do on your own. I think that's usually one of the risks of lectures such as this, because in principle you can build all of these things on your own, but in practice, if somebody else already has done it and you can just buy it, you really should not. So that's another important aspect. And coming to the spirit of the exercise classes, we think it's really an integral part of the whole course. It's not just something we think. It's also related to getting the credit points for the lecture. We don't force you to attend it. I guess you can also watch a recording. But if you care about getting the credits for the lecture, then you'll have to do 80% of the practical exercises. And I guess we're reasonably flexible, so if for some reason you're away a few weeks or something, we can come up with alternative solutions or can make an extra session such that you can do the labs. But yeah, if you care about the points, it's mandatory to do 80% of them. And as you've probably seen at the end of the lecture, even for very simple circuits, if you go through all the analysis, it can become quite tedious, and it's very easy to either make mistakes and so on. So it's kind of low bandwidth learning, I would say. It's something you need to be able to do, but if you just have the circuit and then you wonder like, oh, I'm not sure what this resistor does, then well, you can just take it out and put another one in, or change the circuit on the fly and just measure and test, which is a lot faster. And it's also especially useful because in all the analysis thing we've done here, there's a big nest of underlying assumptions that you make. And if you have a lot of experience, then usually you get all of those assumptions right. And then the analysis matches what you measure in reality. But especially if you're inexperienced, then there are a lot of unknown unknowns in the modeling process, and you kind of leave out stuff that in reality is significant, but you didn't think about it. So if you only do analysis on paper or simulate stuff, then it's kind of risky. So that's why I think it's very important to also have the practical part, because there you'll see a lot of real-world effects and parasitics that are very often relevant, but they're easy to leave out just in simulation or analysis.